All right, well, let's start here. Now, people are surprised when I tell them that there was a time in my life when I actually thought that permafrost was boring. Could you imagine such a thing? Because I think permafrost is great stuff now. I don't know how that change occurred, but I'm very enamored by permafrost. But I'm also concerned about what we're seeing in permafrost, that we're seeing it warm and thaw in places. But what we know is it's very, very difficult to be able to map of what's going on with the permafrost and particularly with the thaw. And so it's great to have today with us one of our experts, Lingcao Huang, who's been doing a lot of work with a number of people here on trying to map abrupt permafrost thaw using space-based machine learning. He's doing work on the Tibetan Plateau and also on the Alaska North Slope. So this is really interesting work. And so Lingcao, from here, you have the virtual podium.
Yeah, thank you, Mark, for the introduction. Let me share my screen. Thank you for having me here. It's a great opportunity for me to present my research and the NSIDC. Today, my topic is about mapping abrupt permafrost thaw from space using satellite images using machine learning algorithm. Specifically, I use deep learning. First, I would like to give some introduction about permafrost and the degradation. Here shows a photo of permafrost, the active layer, and also we can see the ground ice in the permafrost. Permafrost is defined as purely by temperature, with temperature less than 0 Celsius degree for at least 2 consecutive years. Then we can consider it as permafrost. It's a combine of soil, rock, sediments, and also ground ice. Ground ice is quite common, but not always present. And in the northern hemisphere, there are about 24% of the export land underlaid by permafrost. And on the left is a figure published by a paper in 2019. From this figure may shows many borehole observation of permafrost temperature. This borehole they are in Tibet, Arctic, and all this from this observation we can see that the mean annual permafrost temperature is increasing in last 30 decades. Permafrost can result in the degradation of permafrost maintained by shrinking in permafrost area from permafrost to non-permafrost, and also the active layer deepening. The thickness of this active layer increase. And active layer is the layer above permafrost that freeze in winter and fall in summer. And my topic today is mostly focused on the abrupt thaw. And in some literature, they are also talking about some Thermocast Landform. There are several kinds of Thermocast landform. I will talk about them later. Here shows some free photo of Thermocast landform. This one is Thermocast lake. Is quite common in the Arctic. In the continued permafrost region. And these two, one we call it retrogressive thaw stump, and this one, both these two is in Tibet. And this is a thermo-erosion gully. And this point is quite related to ice-rich permafrost. It means that in the permafrost, there are a lot of ice inside the permafrost, and when this ice fall, it can result some distinctive landforms on the surface, and we can use satellite to observe this landform. Compared with the gradual fall from up to down, what I mean up down is from usually the deepening of active layer. this process may take quite a long time, maybe more than 100 years, even longer. But this Thermocast landform, they can happen quite quick. Maybe, for example, the fall slump can, once it is initiated, it can happen, be active for more than a decade. And some like active flare detachment can happen only in a few hours or a few days. This is quite a quick process. That's why we call them abrupt permafrost thaw. Here I like to show you a video I took when I doing field work in Tibet. This video, we can say is a video of fall slump. We can see this is quite. I just use my phone, and you can see from this video, you can see water story come out of water and soil come out of this. We call this place as head wall. Is part of exposed permafrost in an RTA in a fall slump. And on the right is the corresponding satellite images. I will show this video again. Yeah. If you go to the field, you can see and directly the thawing process. So this slide I want to show that the impact of this abrupt permafrost thaw. And on the left is a figure from a paper published in 2016. From this paper, they use an empirical model, consider the permafrost zone and vegetation topography and many factors, and they estimate that in the Arctic, they will have 20% of the permafrost region will affected by thermocast. And on the right, there is two figures shows carbon and also the impact of the permafrost thawing to the local ecosystem. Well, what we know from this research, we can know they maybe have a lot of region were impacted by thermocast, but we don't for the most of the region we don't have real observation. And I will talk about later that there are many non-lake thermocast landform I saw previously for like for example thermo-erosion gully. These landforms, they are quite small, so they only show up on high resolution images. What I mean high is the satellite images with the resolution finer than 5 meters. Yeah, so we have got a question, what's the spatial distribution and what's the evolution of this landform? This is my research and what I want to answer. Before I talk about more, I would like to talk a little bit about deep learning because this is the technology I used. Before, if you're familiar with the image processing, there are a lot of some kinds of called feature engineering. Here is an example so that this is a sober filter is an algorithm that we input image into this algorithm, then we can output the age information. And there are many kinds of this algorithm, more than 100 of them. they input image and output some feature. And in the past, people have to spend many time how to design a good algorithm to programming computer to how to do how to extract feature from images. Then based on the feature, we can identify what we observe, what we can see and observe from images. And deep learning is a kind of technology we input the data into the network, and network it can figure out automatically. This is called automated feature engineering. So it can so nowadays the way we're working with computer is kind of change. We instead of we programming computer to teach them how to do computation, actually we show data to them, then they figure out how to identify targets we are interested. And also deep learning compared to other machine learning algorithms, they have high capability. I think most of you already heard deep learning in many occasions, and this technology has been widely used in many complex scenarios and also achieve unprecedented results. And the reason I think from literature and also other lectures, I think the deep learning they take is taken off because of two factors. One, now people have more data. This is one thing that deep learning benefit from. And also we have more computational powers. So with these two, and we have more data, and because the capability of the deep learning, with more data, other machine learning algorithm, they may in a certain point, they just reach a plateau, cannot improve the performance anymore. But deep learning with more data, they can continue improve the performance. Yeah. This is the data and the main methods I used in my studies. Because previously I said that this landform, they are only show up on high resolution images. So we need images with high resolution, like this one is a planet CubeSat, and these two is the slope and elevation difference from active DM is it have resolution of 2 meters, and I'm also trying to collect other high resolution imagery and try to combine them together. The algorithm I use is from deep learning. There are actually many algorithms for different purposes, for example, for language and for images. And for the image processing, one successful network architecture is called convolutional neural network, and it's very successful in image processing. That's why I use this one. And specifically, I use in deep learning, there is technology called semantic segmentation, and also other called object detection. And here shows two examples of semantic segmentation. For semantic segmentation, this is example, for example, for images. And for semantic segmentation, this algorithm is identify is pixel based. If for each pixel, they give a class label to each pixel, then we can see where is, for example, this one, where is plane, where is the background. And for the object detection, if we, like here, we have a dog, then we identify the location of the dog and give a label, this is the dog. And for the semantic segmentation, I use algorithm, implement the algorithm called the deep lab. And for the object detection, I use algorithm called UVLO. I will talk later. And yeah, and we working on use satellite images to observe this landform. And but the deep learning algorithm actually is they were almost offering are designed for application in our daily life, like we use smartphone to take images, then we tell what's in the images. So there's some kind of gap between satellite images and our everyday images. So I try to build an automatic pipeline then to connect satellite images and this powerful deep learning algorithm. This is the flow chart of my the mapping algorithm. If we for a certain region we may have maybe 10 or 100 landform. Then we in the beginning we know their boundary. Then we consider this as training data. Then we put into this pipeline and also the images cover the same area. Then we put this pipeline. Then we can train the network. Then we after we get a well trained network and its parameter, then we can put all images inside, go through the network. Then we do prediction and to predict where are other similar landform. For example, where are Forstamp and or thermo-erosion gully. And this process is because we need training data, so it is still supervised learning algorithm. Yeah, I made my this pipeline and all my codes are publicly available on GitHub. This is a link. And here I saw some result and case study. Here is a map of permafrost distribution in the northern hemisphere. Previously, when I was a PhD student in Hong Kong, my focus was most in Tibet, and this is some work I did in the past, the thermo-erosion gully, and also the retrogressive Forstamp in the Beidou region, and also the Qinghai Tibet engineering corridor. And now I'm also work on some region in the Arctic, the Alaska North Slope, and also some select site in Canadian Arctic. Let me show some results from my previous study. This is the mapping result of RTS. RTS is a short name for the retrogressive Forstamp. Then from this is a mapping result where I trained and then predict the Forstamp in this region. From this, this is some number related to the accuracy. Here is the in this region there are more than 255 Forstamp, and the algorithm they output they correctly identify 220, but they also misidentified or consider some similar landform, but actually not Forstamp. And there are a few of them, and also they miss some of them. This is called a false negative. And this is the F1, so is a score to evaluate the mapping result. Compared to actually similar studies, this is quite a high accuracy. And I saw some details of the mapping result. The black polygon actually is the is from the manual delineation. We in the beginning we delineated some boundary of Forstamp, and the red one is red one and the yellow one are output by the algorithm. We can see their boundary they match quite well, but we can also see some. This yellow one is false positive. Actually, is not a Forstamp, but the algorithm consider it as a Forstamp. We because we use we try to test the one thing called generalization. Is we train a model, then we apply this model to another study area that never the model the algorithm never seen before. Then we try to see what's the performance of the trained model. And this is a test area. In this test area, actually, we can see the red one. They also collect many. They collected identify many false slumps in this region, and we also can see some false positive and false negative. This two is in the test region, but the algorithm misidentified misled. For the advanced score for this test area is about 0.65. It's relatively slow, a little bit slow, but it's still quite good. And this rise this have so it proves the deep learning can work to another region, even when the training model never seen before. But it also raises another question that you use this algorithm to a new region, the performance may be lower. So this is raises another question about data bias. This is due to the data bias of the training data and the test data. And this is also a frontier of deep learning research. And our objective is not just to prove that deep learning can work and have good performance. Our objective is we have a question we want to answer. So the algorithm sometimes also have some small number of false positive and also some small number of false negative in missing landforms. So we propose a method we call the iterative mapping. And one fact is that we also don't have deep learning algorithm that benefit from many training data, but actually if we focus on new questions and a new question, we don't have enough training data. So we do in an iterative way. We use the training data in this. This is the previous study area. Then we use we already know some false slump, and we have training data there. Then we use them as training data. Then we do training prediction. Then manually validate the output result. Then we make each iteration we can find some new false slump and also some false positive. Then we add some of them to the training process. Then run training prediction again. So in this Qinghai Tibet engineering corridor, we run 9 iterations. Then we after 9 iterations, we cannot find new RTS. Then we finish our iteration. Eventually, if we find 877 RTS in this region. For this region, I think it's good to talk some about the spatial distribution. For the false slump RTS in this region, actually most of them are in the north-facing slope. Here, this figure shows the slope orientation of RTS, and we also do some statistics about their slope angles. For this, for the RTS in this region, they are most of them in the slope that with the quite a gentle slope with the slope angle. You can see here, most of them are on slope angle less than 20 degrees. In some non-permafrost region, the RTS from the previous picture we can see is somewhat similar to landslide, but the landslide in non-permafrost region actually the most happen in a slope with the angle greater than 20 degrees. So from this observation, we can see one explanation is that the ground ice in permafrost actually play a critical, is quite important is kind of controlling factor of the spatial distribution of these landforms. Previously, I used deep learning to identify the location, also their boundary as accurate as possible. And there's another question is that actually this algorithm they don't it's not let I mean it may take times if we use the trained model to predict for example in large region such as entire Tibetan Plateau and Alaska North Slope. For example, for Alaska North Slope, if I have a well-trained model, I use the previous algorithm. It may take a few days to run the prediction process. But another case, if we have like 1,000 or 1,000 GPUs, many computing resources, we don't need to vary. But actually, I don't have a lot of computing resources. Currently, I only use a server with 4 GPUs. So I'm thinking about how to identify this, for example, in large region in a faster way. So I use another algorithm called ULO, and V4 is currently this algorithm have is in the fourth version, and ULO mean is object detection. The accuracy may be not the best, but the speed in terms of speed is the fastest algorithm for the for object detection. In the object detection, this is a test of the algorithm in a relatively small region. We can see the algorithm, it can identify the location of many fault stumps. And this is the algorithm I use then to identify fault stump from here straight. This is here straight is derived from Arctic DM with the resolution of 2 meters. I run a test and for the prediction of RTS for this entire region, is relatively big region. The algorithm can only take 1 hour, then they can finish the prediction process. I estimate if I for the prediction, if I apply this to the entire Arctic, maybe 2 or 3 days, the prediction process may only take 2 to 3 days on a workstation with the 4 GPUs. This algorithm, it didn't outline the boundary, but it detailed us the location of this landform. Yeah, this is a big question. If we have the location, then we can further apply other algorithms to delineate their boundaries. I just finished building up the pipeline using ULO last week, so I don't have more results to show today. Okay. I also like to talk a little bit about the evolution of RTS. Here I show for some in the North Slope and also a for some in Tibet. Here we can see the for some from 2009 to 2020, we can see they continue. We can see the position of this. This is the position of head wall. We can see it advanced to this direction. And this is an example of for some in Tibet. We also can see the head wall. They towards from 2017 to 2019, and we can see the head wall it developed towards the upslope, and this is a boundary of the fall slump from 2017 to 2018. So I also do a little bit of work of trench detection. If the trench is actually two questions. When the fall slump initiate, and if it initiates, how for each year, how many meters the head wall retreat towards upslope, and this is a little to address this question. I also do some work to use one called polygon-based trench detection. We compare the boundary of their boundary in different years, but we need accurate boundary. Then we, based on this boundary, we use graphic computation algorithm called media axis, and use this axis to calculate the retreat distance, like this one. How many meters the head wall retreat and or develop toward upslope. And this is trench detection algorithm is based on polygon base. And I also try another algorithm that use the piezo-based algorithm. Algorithm use a technology in deep learning called Siamese neural network. It compares the two images directly, then try to find out the expanding region. For example, this one is the ground truth, and this is the output. This one is the output from the algorithm. Yeah. One more interesting is that what's the controlling factors of the development of RTS and also some other abrupt permafrost thaw, and what's the future. And this is some idea, but I haven't have time to work on. Yeah. This is my talk today, and here is the summary. Permafrost thaw, they may have other forms, for example, Thermocast lake, and also thermo-erosion gully, and many other landforms. But my research is most focused on the fall slump is one dynamic and important abrupt permafrost thaw in permafrost region. And thank you. I think we still have a lot of time for questions.
All right. Well, this is very, very good. This is cool stuff. So I'll open it up to questions. Who wants to ask a question? I'm sure we have some. I think, Andy, I just saw you had your hand up.
I was clapping, Mark.
Oh, you are clapping. Oh, okay. Okay. Yeah, sorry. I misinterpreted the hand.
Oh, I have a question. This is Kevin. Lingcao, on one of your earlier plots, you showed that in Tibet, the thaw slumps tended to occur more on north-facing slopes, which kind of surprised me. Do you have any physical explanation for why they might occur primarily on north-facing slopes as opposed to south-facing, which would get more sun?
Yeah. In the south-facing usually is warmer than the north-facing, and in this, because it actually is warmer, so to explain this, I think in the south-facing, the active layer is thinner than the south-facing slope, and also in this case, the permafrost table, the layer between active layer and permafrost, this layer may be closer to surface. This layer usually in Tibet may have more ground ice in this layer in between the active layer and permafrost, and because they is more closer to the surface and is more vulnerable to like high air temperature and precipitation. And in this way, it have more possibility of thawing. So this is my explanation for why most of them in the north-facing slope.
Others?
Mark, can I just maybe try to add to this answer and to the question?
Please do.
Yeah, actually, first time I saw this slumps in the Banks Island in the Canadian Arctic, and I was also very surprised that pretty much what I saw, they're all on the north-facing slopes, and that was kind of puzzle to me. And I don't think there's we completely understand why, but I think we should also keep in mind history and previous warm periods, like for example Holocene optimum, and it's possible that some of the ice was already melt during that previous warmer periods, and but on the north-facing slopes they still surviving. It could be one of the reason why they now they were the conditions for developing this process preserved on the north-facing slopes better than on the south-facing slopes. It could be. So it kind of give us, we have to think about not just what's happening right now, but what was in this area, for the last about 15,000 years, and we may find some answers if you look a little bit farther back. So that's just my comment here.
Thank you.
Okay, well, I've just been suddenly called away on something. Kevin, could you continue to field some questions here if there are any in? Sorry, I have to run.
Certainly. Thank you very much, Mark.
Oh, thank you. And Lingcao, this was great. This was just great. This is very, very fascinating work, I think. So I'll see you. Thank you, Kevin.
Sure thing. Actually, Lingcao, I do have a second question on when you're doing the footprint size for the thaw slump in Tibet. You showed some areas where the footprint got narrower, like there's a negative growth. Could you show that plot again? Yeah, a little further along. It's when you figured out area of footprint or area of thaw slump. Yeah, back. Yeah. No, next one. Yeah, right there. You showed it shrinking on panel D, and it struck me that seems a little odd, given the way that the ground erodes and subsides. How could it shrink? Is that possibly some sort of size error in the different photographs or different images?
For this expanding area, this is the thawing process of the fall stump. I think maybe some distortion of images, but the image distortion is minor. I think in this case, we can see the head wall here, and previously this. In my previous video, we can see the thawing process, and suddenly the thawing process, the soil and water they just fall and run away, and this head wall they move forward towards upslope.
Okay, I think that kind of answered my question. This is a very interesting process for getting errors. We got a question for you from the chat, from Doug Haller. Doug, do you want to just ask a question, or should I just read it?
I can. Let me. I didn't so.
Go ahead and read it. I just posted it there.
I am new to NSIDC, knowing little about permafrost. Is there any way that degradation could be reversed? I think there's lots of opinions on this. Lingcao, you go first.
Degradation. I did some read some a few paper or talk later about how to reverse and protect permafrost. They for example, the vegetation cover and how to cool down, but this I think this is quite complex. I'm not sure I can answer this.
I'll throw out an opinion, then we'll ask
Can
Vladimir.
I can try. It could in some cases, and it cannot in other cases. And also we have to kind of be clear about the time scale we are talking about. So on a time scale of decadal or even century, with colder climate coming, or for some reason, I don't know, for any kind of reason, permafrost can aggrade and develop in the places where it is degrading now. I mean, when it's thawing and it will freeze, it can freeze. Now, the question is how much ice will be accumulated in a new growing permafrost. And here we come to the point that degradation of this massive ice, which was sequestered in permafrost for the thousands and thousands and tens of thousands of years during the last glaciation or previous cold ages, to put it back with colder climate, it will take pretty much the same amount of time, so thousands of years. So if you're talking about on the time scale about decadal or even century, this degradation of this icy permafrost with massive ice in it is not reversible on this time scale, even if climate will be colder and permafrost may be reestablished at some locations. It will definitely take lots of time, new ice age pretty much, to put similar amount of ice in freezing ground. So that's kind of question. So on one, in kind of cases when climate colder, you can restore permafrost, but probably on a time scale of century, you cannot make this ice-rich permafrost. It is impossible. So reversible and irreversible.
Thank you.
Yeah, I would add to that when you see degradation like this, where you have a large amount of mass that's moved horizontally, that's pretty much irreversible. Even if the permafrost refreezes, you can't put the dirt and ground back onto the hillside.
Well, like I said, if a new ice age will come, it may happen. I mean, it may develop depending on what kind of ice it is. For example, it is buried glacier ice. Well, you develop new glaciers in the same place, and then glacier will be covered with frozen material. So you can do it, but you need about new ice age, about several tens of thousands of years to restore it. And of course, it is impossible on the century timescale.
We have another question that came in the chat from Twyla.
Okay.
I'll just read it.
Okay, thank you.
I'm wondering about the range of impacts from these changes, for example, water, infrastructure, etc., and which impacts appear most common or urgent. Is there a need for prediction and warning? Or are questions more about processes? Lots of regional variability in impacts, or no? All right, Twyla, that's actually about 5 questions, but we'll let Lingcao answer as much as possible.
Okay. First, I talk about the impacts. In my introduction session, I list some. I give some example of published papers that talking about the impact for the carbon release from permafrost, and also the impact to the local environment. You can see something frozen in permafrost now released to the local environment. So this is and for our work in the Tibet. In Tibet, engineering corridor actually lays loads and also levees. And for someone like close to these infrastructures, it does have impact to the safety of these infrastructures. Yeah, so for that region, people monitor this permafrost thawing next to the low closely. For the, I think there is a need for the prediction and warning. But the question is how. Yeah, for some infrastructure, they may put some monitor and some equipment or like GPS and something temperature monitor to monitor this the permafrost real time. And yeah, we also quite interested about the questions because how was the process, and we try to understand the past, how this for example when they initiate, what's the controlling factor, and what's the we found or we try to observe things as many as possible and try to understand the process. Try to understand the past, then we can you can use our understanding to predict and the future was the future will like, and also the regional variability. Yes, this my thought.
Yeah, there are other questions. I would only say your work on controlling factors would be a huge part of future prediction.
Yeah.
I got a question from Gabby Calo Barrios. Hi, Lingcao. I am working in a project in which we need to identify avalanches from LiDAR data. Do you think that your method could work for avalanches?
For my colleagues, they also use my method, my script on GitHub to map landslide. And if we this is kind of a computer vision problem. If we human can see something on images, no matter is obvious or is subtle, if human can see, then this technology can do that.
Yes, Lingcao, aren't you working with Christy Tiempo and similar type techniques?
Yes, I will use the same techniques to, but I haven't started to for the fronting area from star images, and also some landslide from high resolution images. We because the beautiful of the deep learning algorithm is that we use the same pipeline, but we use so different data to computer. Then computer can figure out automatically.
Okay, Gabby, I want to suggest that you contact Lingcao and start talking directly. We have another question from Ron Weaver. To what extent can retrogressive thaw slumps feature detection and monitoring be related to general or regional permafrost health? Could this RTS AI technique be a way to assess changes in a regional permafrost assessment? And the last part is, I presume INSAR is too low a resolution to be used to map retrogressive thaw slumps, but if it is not, is it a data set of use? And I could answer maybe the last part. Why you tackle the first part?
Okay, I will answer the first question. If we observe RTS in a specific region, we can conclude that the permafrost degradation is happening there. But how much of permafrost is degradation? I don't think we cannot directly answer, because the thawing of artists is also related to the ground ice, but this is something we don't know. What we can just know is that, yeah, we observe this and we can say the permafrost degradation is happening there. For the side image, yes, the side images, the resolution is quite coarse. Yeah, so I didn't have INSA result for mapping, but there are also some many work of INSA to monitor the permafrost health from INSA techniques. I think Kevin can give some examples.
Yeah, actually, we INSAR does have the spatial resolution to map individual thaw slumps, and we have used it to map as low as 5 to 10 meters. And but the problem there is not the spatial resolution; it's the temporal resolution. Trying to get enough INSAR images to cover a long enough time period that you could really detect the thaw slumps. People are working on that right now. We got more questions. I'm going to zoom through them so we can get them all without going too far over. Go Awahana asks, how do snow covers and patches influence the results? Do we need to eliminate images with snow surface in the thermocast features?
The short answer is no. If we cannot entire thermocast landform is covered by snow, we cannot see anything from that. Then if human cannot see first thermocast from the images, then we cannot use that images. But for some cases, there are only not a very thick layer of snow. Sometimes they have snow, but we can still see this landform. Then we can still identify the RTS and other related thermocast landform.
All right, Gabby says she'll contact you later. From Lingcao, and I hope I pronounced that right. It seems your method primarily relies on imagery, and I'm assuming you mean visible or infrared. Yeah. Do you think it can include other variables like terrain factors such as slope or temperature?
We did include the terrain factors. In our work in Tibet, actually, we use the terrain factor in the post-processing to remove some false positive. And for my country work, because previously I saw you, we can observe. We can observe some features. For example, this is a slope, and this is an elevation difference. Arctic DM actually they have multi-temporal observation, so we choose the newest one and the oldest one. Then we do a differencing. Then we also can see some features from this topography derived data. Then we human can see that. Then we can use algorithm to detect them. For the temperature, currently I don't include temperature. This is is still a computer vision problem. So I'm not sure how to include temperature in this algorithm.
As a suggestion, you might consider temperature as one of the controlling factors.
Yeah, controlling.
Especially summer temperature. Summer temperature could help.
Yeah.
And precipitations also.
Yeah. This is some controlling factor we need to consider in the future.
All right, dude. We've gotten a lot of very good questions today. Are there any more questions for Lingcao? All right. Well, I wanted to say thank you, Lingcao, for a very interesting and very nice presentation on your thaw slump work. I encourage anyone who has further questions for Lingcao to contact him directly. And I'd like to say thank you again to Lingcao, and I thank you, all of you who were able to attend today. We really appreciate coming to the seminars. Thank you very much.
Thank you, everyone. Thank you, Kevin, Miss Tia.
Thank you so much.
Thank you.
All right, well, we'll see everyone next week at our next seminar. Miss Tia, what's our topic next week?
Actually, our next one right now is scheduled for the end of May.
Oh, all right. I didn't quite realize that. I go to these every week. What is the topic? Do you know?
ISAT-2.
ISAT-2, LiDAR. Excellent topic. All right. We look forward to seeing everyone at the next seminar in, I guess, 3.5 or 3 weeks. So everyone take care and have a nice and healthy day. Thank you.
Thank you.
Thank you.